Fourth and final session today, which will deal with applications and challenges in health and behaviour. And the first speaker is Rama Cont of the University of Oxford. And he's going to talk about classification and monitoring of trading strategies.
Thank you, Tom. It was an idea of Terry for me to give this talk here. So at the risk of being the odd one out, I'm going to discuss about something which looks totally different from all the other topics discussed today. It's related to finance. But in fact, listening to the talks today, especially the talk on Alzheimer, I noticed that many of the things I would say are exactly similar. So you will see the similarities, and I guess that's why he wanted me to give this talk. Okay. So what is the problem that we're interested in here? So we're interested in developing quantitative tools for monitoring financial portfolios. And the context is that in financial markets, you have a lot of the market participants engaged in various complex trading strategies. So these participants can be humans or robots. And they deploy a wide range of trading strategies which we don't know, but they impact the risk of the institutions where these people sit, and they impact the risk of the market. So there's a large activity deployed for the risk management and compliance of these trading strategies. So most strategies used by market participants, and I will give some examples, are dynamic strategies. There are a set of trading rules which say if the prices behave in this way, buy or sell this quantity of shares or bonds or whatever. And these rules intervene at various frequencies, so this leads to portfolios which strongly vary in time, and the risk profile also strongly varies in time and depending on the behavior of prices. So if you look at these portfolios, and I'm going to give some examples, you will see typically, they have complex path-dependent dynamics. They react to the behavior of prices in a path-dependent way. And this makes the risk analysis and the monitoring of these portfolios quite difficult, even ex post. By ex post, I mean if you have a fund manager who runs 4 or 5 different strategies, and at the end of the month, for example, he makes some money or maybe he has a big loss. Even ex post, it is not easy for them to understand why they made a big loss that month, why they made a big profit the other month, because the strategies are intertwined. They involve the same stocks or the same bonds, and so performance attribution ex post. We're not talking about forecasting here. Even analysis, forensic analysis of the performance of portfolios is not simple. So here I'm going to just look at one aspect of the problem, that is the risk calculations for portfolios. So basically, you have a trading strategy that is trading in several financial instruments, say stocks and bonds, and you want to evaluate the risk of this portfolio over some horizon. Okay. So typically the way it's done now, both at the small scale of a bank and the large scale of the regulator, the central bank, when they do bank stress tests, the way it's done now is that you look at the snapshot of the portfolio at a given time, so today, and then you have a statistical model for the ingredients of the portfolio, stocks, bonds, currencies, whatever. Based on this statistical model, you simulate project the scenarios into the future horizon. For example, if you're interested in the risk of the portfolio over 1 month, you simulate 1 month horizon scenarios for everything in the portfolio, and then you do linear combinations of these instruments based on the portfolio weights. But today, this gives you an evaluation of the loss of the portfolio in each scenario, and then you build the loss distributions by simulation from that. So this is what I call loss estimation based on a static snapshot. Okay, so you simulate the ingredients of the portfolio forward, but typically model them as stochastic processes, but the portfolio itself, you freeze it at time t today because that's all you have. Now, another situation is where you are the portfolio manager. Instead of being a third party who's monitoring the portfolio, you design the strategy so you know perfectly how the portfolio is going to react in such and such scenario, because there's a formula which you devised, which tells you how the portfolio will behave in each scenario. So you can do a full simulation. In each scenario, you can simulate both your portfolio and the prices of what's in it, and then you can do what I call a scenario simulation for a fully specified strategy. So these are the two ways that are currently used for risk analysis of portfolios. The first one is based on a static snapshot of the portfolio today, so it does not account for how the portfolio may evolve in the future in each scenario, because we don't know. We only know what's in it today. The second approach does account for how the portfolio will evolve, but that requires knowing how the portfolio will evolve. So this is only available to the portfolio manager himself or herself. It's not something that a third-party risk manager or a regulator can do, because they have no idea how you're going to change your portfolio. And these are the only two approaches available. I do not know of a third approach. So let me explain a little bit about the problem in more detail. So we're going to talk about portfolios. So what are portfolios? So think of a market with D financial instruments, stocks, bonds, currencies, whatever, with prices that I call S1 to SD. So these vary as a function of time. So typically they're modeled as stochastic processes, but here we can think of them as paths. And now a portfolio is the specification of how many of each instrument I hold at each point in time. And so I call phi I the number of shares or contracts of I, and the value of this portfolio is simply sum over all instruments of number of contracts times the price of each contract. Now a trading strategy is giving a rule for how this portfolio will evolve in time, and obviously at each point in time t, you can only use information available up to that point t in a causal way. So this is what I call a non-anticipative specification. It's a non-anticipative rule for saying at each point in time t how many of each share you hold. Okay, and there's some points in time t where you will change the composition of the portfolio. These are the trading times or the transaction times. So they're called TI. So in between TI and TI plus 1, you hold some portfolio whose composition is computed at TI, depending only on the information available up to time TI. So that's any trading strategy is of this form. There's no restriction here. Now to simplify, I will consider in my talk, in the examples, trading times which are on some fixed time grid, but you can also consider in this framework trading times that depend on the path of the price. For example, whenever the price hits some level, I trade or something like that. Okay, so now, from these strategies, we're going to focus on a subclass which makes them comparable, and these are self-financing strategies. So a self-financing strategy is simply a strategy where, apart from trading by buying and selling, I don't do anything else. I'm not injecting capital or consuming any cash or removing cash from the portfolio. So the variations of the portfolio are completely determined by the variations of prices of things in the portfolio. This makes the portfolio value a functional of the path of the prices of the things in the portfolio. And that's the starting point of this analysis. So for a self-financing portfolio, the only thing that makes the value of the portfolio go up and down are the variations of the components of the portfolio, which means the paths of the components that I call S1 to SD. Okay. So in general, okay, so let me give it an example here to just motivate what I'm going to say. So there's a typo there on line 2. So an example of a strategy that is very common, so this gives you just an idea of how these strategies are specified. You look at some linear combination of different instruments in your portfolio. For example, it can be the difference between two stocks. So say you think that Coca-Cola and Pepsi-Cola are very related together. So you think that the difference between Coke and Pepsi stock cannot go to infinity or to zero. It's going to remain in some zone. And so that means you think that this difference is stationary. Okay, so you're going to estimate, this is a very commonly used strategy, it's called pairs trading. So you estimate a moving average of this difference. So this difference is what I call y here. And then you estimate a moving average standard deviation of this difference. And then you say, well, if this difference deviates from the moving average by more than a few standard deviations, then I'm going to, well, for example, if the difference is Coke minus Pepsi, if the difference is above the moving average by a standard deviation or more, then I will buy Pepsi and sell Coke because I think that is going to go back, and the opposite if it's below. Okay, so that's a simple strategy. And then you can put a limit on how much you can take a bet on this. The bet size can be limited typically by some cap, which I call K here. So you can go up to K or down to minus K in this bet. Okay, so in this example, which is a trivial strategy used widely by traders, the portfolio value and strategy performance will depend on some features of the path. What features of the path? Well, they depend on the paths that intervene in the linear combination through their excursions, the excursions of this particular linear combination away from its long-term mean. And this long-term mean does not need to be well specified. There is no reason why this is actually the mean, so it may actually be completely wrongly specified. So there is some function m, which you can make from the moving average, the path-dependent function. And then you have another function which is y, and this depends on the excursions of y away from m. So this is an example, just to show that trading strategies that are very simple to specify lead to portfolios whose performance is a complicated path-dependent functional of the underlying price paths. So the analysis of these portfolios is fairly complicated, especially if you don't know what's going on in strategy. If I know exactly what the rule is, of course, I can simulate these paths. If I know the strategy and I know exactly the distribution of everything involved in the portfolio, I can simulate scenarios, run the strategy along the scenarios, and get some loss distribution for my strategy. But the problem is, if you're a risk manager in a bank, you monitor hundreds of traders, they're doing things like that, but you have no idea what they're doing. The only thing you see is the final value of the portfolio every day. You can monitor them on a regular basis. You see the value of the portfolio, but you do not necessarily track the components in detail every day. So strategies like this lead to complex state-dependent risk profiles. And this means that if you start from two portfolios which are exactly the same at time 0, if they do not correspond to similar strategies, there is no reason why at time t they will have the same profile. So if you're at time 0 and try to estimate the risk of your portfolio at some horizon t, well, simply the snapshot at time 0 of the portfolio does not give you a good idea of what the risk is, because unless it's a buy and hold static portfolio, you're not capturing what happens to the portfolio when you move. So in other words, when you do a static analysis based on the current snapshot of the portfolio, what you compute is what's here. So you look at the portfolio weights times 0, and you take the sum of portfolio weights at time 0 times the variations of your portfolio components as seen through a model that you simulate from. But actually, your actual portfolio loss is, well, the value of the portfolio at time t minus the value at time 0. This is the true gain or loss. And so this, if you decompose it, well, you see that it's this number above plus an extra component, which is, of course, the variation of the portfolio itself from now until t, which we don't know unless we can relate it to something which is the behavior of the underlying path. Now, this may seem impossible to tackle, because if I only know the portfolio now, what can I say about the future value of the portfolio at time t? This seems hopeless. Except that in systematic strategies, the way they are built, the portfolio reacts in a systematic way to the variations of the paths of the components of the portfolio. So the idea is that we're going to represent the portfolio itself as a functional of the underlying paths of its components. And if we can estimate in some way this functional dependence, then we can not only compute this, but compute also this component. And it turns out that for dynamic strategies, this second component is at least as important as the first one. And in some cases, the first component here is the only one, because this component can actually be zero. For example, if you look at many high-frequency trading strategies that are used in electronic markets nowadays, so typically these strategies are portfolios which start at the beginning of the trading day from a position 0. So there you have 0 shares in all of the stocks. And then you start buying and selling. You buy and sell during the day in a specific way, following an algorithm. And at the end of the trading day, you close your position, you sell off everything, and you end up with 0. Okay? So if you do a static analysis on this portfolio, the starting portfolio is 0. So 0 times anything is 0. So you're going to the risk is just invisible to a method which is a static portfolio approach based on a daily snapshot, because the frequency of the trading is much higher than daily. So a daily snapshot will not see anything. So that's what I mean when I say that the risk of strategies with frequency higher than the horizon here is not visible unless you look at the first term. But of course, the first term will be everything that you want to know. So how are we going to do this? Well, an idea here is that, well, if you look at this portfolio gain and loss for a self-financing portfolio, it's actually an integral or a sum of the increments of the prices in the components of the portfolio multiplied by the number of shares. So it's an integral along this path. So it's completely determined by the price path. Unfortunately, unlike a buy and hold portfolio where the change in the portfolio is simply number of shares times the change in each ingredient, for a truly dynamic portfolio, it's really an integral and it's not just a multiplication. So it cannot be expressed simply as a linear function of the price increments. That's why the static simulation fails to see what's going on, and we saw that there's a missing term. However, as you saw extensively during the talks by today, a very nice idea is to, instead of trying to express everything in terms of price increments, as is done in the static approach, to express these functionals in terms of the path signature, which has been defined by today in all the talks. So, and that is defined as a sequence of iterated integrals. So you start from the increments as the first component of this sequence, and to compute component k plus 1, you integrate the component k against the price path itself in this tensor form. So it means that, for example, the second component is the iterated integrals of s against itself, and then the third component is iterated integrals of three components, three of the product of three price increments, and so on. So the idea that I'm not going to repeat because it was extensively discussed in the talks this morning is that you can express fairly complex functionals of price paths as the linear functions of the path signature. So I'm going to come back to this in a few slides. But just to understand why this is a natural idea in this context. But for example, if you think of this strategy that I showed you earlier, this pairs trading strategy where you trade one stock against another. Well, in general, if you look at a pairs trading strategy, the loss of a pairs trading strategy can be a complicated function of the paths of the pairs you're trading. So the two paths specifying the prices of the pair and how many times they cross and so on. However, if you take away this cap that I put, I put a cap on the strategy that is a nonlinear term. If you take away this cap, then the outcome of a pairs trading strategy can be expressed fairly explicitly as a linear function, in this case, of the level 2 components of the path signature, so what we call S1 and S2, and only involving the pair ij. So in this case, in this very specific case, we know that although it depends on the entire path in a complicated way, if you don't look at the path as only through its increments, but also through these multiple integrals, then you can linearize this relation in a simple way. Now, in general, that's not the case that we can work out this explicitly, but the idea that is, but due to Terry Lyons, is that if you first spend the effort of unfolding the path into its signature, what we call the path signature, so this is a nonlinear operation because you start from the path and take these multiple integrals, so it's an effort that you have to deploy initially, but once you unfold the path into its signature, it's a much larger object, then these functionals that we're interested in, we can express them in a linear way in terms of this larger object that is the signature. A way to think about it, if you're not familiar with this, is to think about the analogy with Taylor expansions, okay? So if you take a function and then you expand it in a Taylor expansion, okay? So you're expanding it into these polynomials. Now, once you've expanded it into these polynomials, now various operations which were nonlinear initially now become linear once you know the coefficients of this expansion. So here you can think of it in a similar way, but here instead of looking at one point, we're looking at the entire path. So quantities that depend on the entire path can now be expressed as linear functionals of the elements of the signature. Now, in particular, what we're interested in here is to apply this idea to the value or the terminal profit of a trading strategy. So as we saw, for any trading strategy that is self-financing, the value can only be a functional of the path of the underlying prices of what's in the portfolio. So now where we're going to apply this idea, we're going to represent it as a linear functional of the signature, and that means, so the signature is simply a sequence of elements which are the signatures of at level 1, 2, 3, k, etc. So if we call, having a linear function B means that there's a linear dependence with respect to each component of the signature. So in general, it can be represented in this form, where delta k is a tensor of the same dimension as the kth element of the signature. It's a measure of the sensitivity of the value of the portfolio to the kth level of the path signature of the underlying path, which corresponds to the components of the portfolio. So the delta k summarizes how the variations of the path from 0 to t of the components are transmitted into the portfolio, and so it's an object of the same dimension as the kth element of the signature. So we call this sequence, the delta k's, we call this the signature of the trading strategy. And if we know the signature of the trading strategy, so if we know the sensitivity of the value of the portfolio to a change in the kth element of the signature for all k, then we can reconstitute the loss and gain of the strategy. Now, the good thing is that this can be estimated from data on the underlying path through a linear regression analysis. So the idea, just as in the talks this morning that you saw, we start from observations of the underlying paths of the components of the portfolio. From this, we estimate a discrete counterpart of the n level of the level n signature, exactly in the same way as you saw in the earlier talks. And now I'm going to truncate this at level n. I'm going to write the term that I'm not including as an error term, and we treat this as a regression model. So I can now estimate the sensitivities to each component of the signature by a regression. So that's what I'm going to do exactly. Now, the important point is that this does not require knowledge of the strategy that's driving this profit or loss, and it does not require but knowledge of the portfolio positions. I'm regressing the value of the portfolio at horizon t on the signature of the path over the same horizon. Okay, so this leads to a concrete estimation method that we call SASE. I mean, in statistics, I've learned that you have to have a fancy acronym, otherwise it never sticks. So you take the price paths and the value of the portfolio that you're trying to analyze at the same sampling interval. Then you compute the discrete path signatures for the underlying price path up to level n. Okay. And then you regress the portfolio values on these path signature features. Path signature features means the components of the signature viewed as a vector. Now, since we're in high dimensions, typically if you look at the level n signature, the number of components is d plus d squared plus d to the n. Well, we're going to use a machine learning approach, which is typically here in this study we use the least absolute shrinkage selection approach, the lasso. This is very straightforward. So basically it means instead of doing plain ordinary least squares regression, you do a L1 penalty, which tries to force as many coefficients as possible to be zero to give you a sparse regression. Important thing is you do not require knowledge of the strategy, you do not require knowledge of the portfolio positions, you regress the value of the portfolio. So this can be done in a blind way. So let me just end with an example to show how it works. So we had the data from various portfolio managers. And so here I'm going to show you an example of a multi-strategy portfolio, a portfolio manager running 3 different strategies using different European stocks over 4 years. So there's a lot of stocks available to this manager, but he's only using strategies involving 3 or 4 stocks, but we don't know a priori which 3 or 4 stocks in each sub-strategy, and we do not see the profit and loss of each strategy independently, but only the total portfolio loss. So the question is, can we disentangle the performance of the portfolio into its different strategies and identify their components? In other words, can we reverse engineer what the guy is doing from just his portfolio performance and knowledge of what he's using in the portfolio? We need to know the universe of instruments, but not the positions. The answer is yes. This is exactly what the method does. So how does it do it? First, you apply the regression analysis to the signature of everything in the portfolio, and you regress the total by changing the portfolio value over each day on the daily signature of the stocks in the portfolio. So what you see is on the right. What you see is the coefficients in the lasso regression. So you see that most of the coefficients are very close to zero. It identifies a handful of coefficients corresponding to less than 10 stocks. So it says that the performance is mainly concentrated on less than 10 stocks. So the weights, the first few coefficients are the level 1 signatures, then the level 2, and so on. I don't have time to go into detail, but basically, first you see which ones are non-zero. Then you look at all the pairs and triplets IJK, such that there is at least one coefficient in the signature which is non-zero, which links them. This defines a graph. The connected components of the graph can now be identified as sub-strategies or sub-portfolios which the portfolio manager is running. So first identify the non-zero coefficients, then look at the connected components of the graph. There you have now a good picture of what the guy is doing. And in this case, there are 3 connected components. It seems that he's running 3 strategies. And you can then further analyze the strategies. For example, if you analyze the first connected component, you see that it only involves 2 stocks. And the only things that you see in the signature graph are the first here what you see is the level 2 component that connect the 2 stocks, and here you see one level 3 component that connects the 2 stocks. So here you see that it involves it is exactly a pair trading strategy involving stocks 1 and 2, for example. So this I identified just by looking at the total per portfolio, the gain and loss, without knowing what the strategy is doing. Okay. Now, one application of this, once you see this, is that now you have a linear way of saying along such and such path, this is how my portfolio will behave, because I have a way of computing the signatures of each path. Then I apply this linear combination. This gives me a linear approximation to the value of my portfolio along such and such path. So this gives a dynamic way of simulating the portfolio loss forward. But unlike the static approach where I look at the snapshot of the portfolio and assume it's going to be the same from 0 to t, now I can transport it along these features. And if you look at, for example, something simple like a 5-day ahead estimation of loss quantiles, with the static approach here for this strategy, which is quite dynamic, you get a 40% average relative error because the portfolio is constantly changing. With the approach that I just described, if you now approximate it by this linear combination of signatures, so basically the first approach is only looking at the level 1. Here we go up to level 3. You reduce the average relative error to 5%. So that's some concrete application for loss simulation. So let me stop here. So basically what I've tried to show is that if you use path signatures of market prices as features for analysis of dynamic trading strategies, they lead to, they give you a framework in which you can now deploy tools like linear regressions, simulation, and so on, which are used classically in a static framework for portfolio analysis without any extra technology, without any complicated new concept. You can deploy them now in a dynamic setting, but you have to, at this extra cost of unfolding your portfolio into viewing your portfolio now as a functional on this large sequence of features that are the components of the path signature. And I showed you through an example how it can be used to dissect a dynamic strategy, really understand what's going on here, and it leads to a strong improvement in the accuracy of loss simulation methods, because you're accounting in some way for the variations in portfolio weights. And the most important thing is that to do this, you do not need to know the details of the strategy. So you only look at the value of the portfolios. So this can be used in a blind monitoring of portfolios. Blind meaning not in a bad way. Blind meaning you don't need to know what's going on to do the monitoring. You just do regressions, path signature calculations, and regressions. You don't need to have any extra information than the value of the portfolio. So here's a list of potential applications.
Maybe time for one question. Quick question. Yes.
If you're using this for your blind automated monitoring of portfolios, do you have any sense yet of how wrong could you get it? I mean, I'm worried that you might cope with with
so
occasions but miss the crisis.
Yes. So the static approach, which is currently used by everybody in the monitoring of portfolios, except for the portfolio manager who knows what he's doing, that one will miss completely any variation of the portfolio composition during the horizon of simulation. So it's obvious that this is an improved approach over that. But this assumes that the way your portfolio weights are going to react from now onwards is the same way that they have been reacting to price variations in the past, because I'm using the past data on your portfolio behavior, so I'm assuming it use the same strategy as in the sample data set. If you suddenly switch strategies right now, well, of course, it's going to go wrong. So for example, if you've been hedging your portfolio, and that's what I estimate when I look at the signature, and all of a sudden you stop hedging, you decide that you're going to have a big directional bet on something, obviously this is not going to capture. So it's going to capture statistical regularities that relate the portfolio to the underlying path.
Okay, well, let's thank Rama again.